First of all, we have to understand the difference between these situations when a capacitor is charged or discharged. That means nothing is happening anymore inside it. So that means the voltage across the capacitor doesn't change anymore, and there is no current through the capacitor. However, if a capacitor is charging or discharging, in that case, the voltage changes over time. There is a current through the capacitor. And when the capacitor just starts charging, that means at t equals 0 at initial time, there is no charge yet, so the voltage across the capacitor is 0, and the voltage is gradually increasing from 0 to its maximum value, which might be equal to the voltage of the battery or not. And when the capacitor starts discharging, that means it has some initial charge, and the voltage changes from its maximum value to gradually to some final value, which in general could be not equal to 0, but in our problems normally is 0. And before we actually do this example, let's take a look at the experiment. Not sure if it helps, but what we have here is a simple circuit. There is a battery, and the switch, which is closed, and the resistor, 10,000 ohms capacitor, and now the circuit is closed, which means the capacitor is charged. So I'm going to discharge it initially, and also I have this interface connected to the computer. Most of you have seen it already in the lab. This Plugger Pro interface, which we can use to measure current, voltage, or temperature, or pressure. Different sensors could be connected to this interface. And here we can read live data. Well, first of all, I want to discharge the capacitor. So first I want to open this switch. I want to take out the battery. Of course, I need to connect the circuit back, and when I close the switch, it's going to be closed. And let's see if it's going to work today, because I tried it 3 times. Monday, Wednesday. Hey, it is working. It's amazing. Well, physicists, engineers have been working for a long time, for decades, to develop a device like that. About 10 years ago, it would be huge and cost thousands. Now, practically anybody can buy a thing like that and do measurements. Well, if you're a fan of doing and making measurements. So what do we see here? The capacitor had some initial voltage. Well, in this case, it was equal to the voltage of the battery. And when I close the switch, the voltage across the capacitor eventually get to 0. And what is happening to the voltage across the resistor? Well, as long as I close the switch, it jumps to the maximum value. And then again, it gradually goes to 0. Why? Because when capacitor discharges, it loses eventually all the charge. At its initial instant, we could treat the capacitor as a battery. So we could apply Ohm's law of voltage, resistance, and current related. Now let's take a look at the same situation when capacitor is charging. And first I had to open the switch to prevent the capacitor starting from charging immediately. I have to connect the battery back, and let's see what's happening now. So the capacitor didn't have any charge initially. It was completely discharged. No charge, no voltage, because Q equals CV. And that means the capacitor starts charging from zero voltage and eventually it reaches the maximum value. Well, we actually now can figure out how all these variables change over time. This software allows us to do that. For example, I can try a simple linear fit. Doesn't really work. That black line represents my trial and it doesn't fit the actual curve. So I can try, for example, a quadratic fit. No better. Well, physicists know doesn't really work. Let's try a different function. Sorry. Here. No. Where is it? Yes. Here. Exponential function. And we can see the curve is fit. And the coefficient, which describes how fast the voltage changes over time, that number C equals roughly 0.2. And of course, we can repeat the same procedure again and again. You've seen the slides on Wednesday. That's how I got it. And the last experiment I want to try with this setup. First, I want to charge the capacitor again. However, it is charged now. So first I have to discharge it. How can I discharge it? I just have to take a wire and connect the terminals of the capacitor to each other. And if you look at this number, now it's 0. Where did the energy go? The capacitor had the energy. Charge times voltage divided by 2. And now there's no charge, no voltage, no energy. What happened? Does it mean it just disappeared? Well, a law of conservation of energy says energy cannot disappear. So what happened is here, the energy gets lost. This wire gets a little bit warmer than it's been before. That's it. So this energy gets lost in heat. Well, okay, this is open. This is discharged. What I want to do, I want to double the resistance. I have this decayed resistor like in your lab. And now, okay, everything is ready. Doubling the resistance should change something. Let's see if it actually does change something. We can see that now it decreases, but decreases slower. It takes more time to drop the same amount of voltage. And we know how to relate the resistance, capacitance, and time constant. I just want to show you. It's not a mystery, not magic. And this capacitance now is 0.1. It was 0.2. Now it's 0.1. Well, any questions? In that case, let's move on and solve a couple of more problems and finish this. Okay. Here, a 9-volt battery, a resistor, capacitor, initially uncharged, and switch. So the top picture shows your initial situation, and then we close the switch. And it turns out that if we wait for 4 seconds, the voltage across the capacitor becomes equal to 3 volts. So it was 0, now it's 3. So we know what to do. When voltage changes, when capacitor is charging, the function which describes that change over time, the known function, exponential function. What we know is that at t equals 4 seconds, the voltage across the capacitor equals 3. So when we write that equation, we just plug in all the numbers we know. Only one variable is unknown, is C, the capacitance. And we solve it for the capacitance. The only mathematically tricky part is solving the exponential equation. When the unknown is in the exponent, to solve that equation, we have to apply a natural logarithm to both sides of the equation. So if we apply ln here, ln and e cancel out each other, basically like calculating square and square root, multiplying and dividing. In this situation, if we write ln here, it doesn't change the equality, because in mathematics, wherever you do to one side and you repeat to another side, it doesn't change the equality. Now, ln and e kind of cancel each other out. What's left is this. And now we can solve for capacitance. Pure mathematics, no physics at all. Start from a correct equation. A correct equation is that one which gives initial voltage 0. So that's a check. If you plug in t equals 0 and we get voltage is 0, that's the correct equation. And this works for this. If time equals 0, 1 minus 1 is 0. So that's the right equation to use. The rest is mathematics. Well, this is my first question to you. We know, because, well, how do we know? We can read that it takes 4 seconds to reach the voltage equals 3 volts. So the capacitor starts charging from 0 volts, and in 4 seconds, the voltage equals 3. The question, how much additional time should we wait until the voltage across the capacitor reaches 6 volts, doubles? All right? This system is working today. What a beautiful day. Everything is working so far. on Tuesday, I will hide something very expensive under one of these chairs. Whoever first finds it, keep it. All right. Let's see what you think. The graph is supposed to help you, because if you look at the graph, it actually gives you away the answer. And here, this is how, does it work? This is how much time we wait to reach 3 volts, and this is how much time we wait to reach 6 volts. So we can see it takes more time. Interesting. This screen alternates that software. So the answer is it takes more time. And if you want to wait even more, for example, when it's gonna reach 9 volts, how much time should we wait? Well, mathematically, this line never touches, well, the value equals 9. So mathematically, it's asymptotically approaching that line, and mathematically we have to wait infinitely long time. Of course, well, it doesn't happen in real life. So mathematics doesn't describe absolutely accurately what's happening in real life. In real life, it's something like this is happening. And eventually this voltage is reached, but mathematics shows something a little bit different. So to estimate the actual time, we just use the time constant. It's a good enough number. If you wait time constant, the voltage changes in E times, which is good enough. Well, now if we want to discharge a capacitor, we just have to use, again, a different equation. And at initial time, when t equals 0, the initial voltage is supposed to be equal to the maximum voltage, and then it gradually changes. Well, the last problem related to capacitors. Now we have a little bit more complicated circuit. It has 2 resistors. Well, what can we say about the capacitor now? Well, this potential is 0. This potential is 24. Is there, or there is no current in this circuit? If you think the current presents, you will press 1. If you think there is no current in the circuit at all, please press 2. And well, it's a 50-50 chance. You just have to follow the charges. If they have a way to start and end at the same time, there is a circuit. If there are gaps everywhere, there is no current. What do you think? What did you answer? 2. And what did you answer? There is no current.
I don't know.
Answer 2 says there is no current. Answer 1 says there is. So there is this means, well, it means my system is working again. So the answer number 2 means there is no curve. And we just have to look at the, so that's 0, that's 24. Charges, fictional positive charges, not electrons. Yeah, electrons travel in opposite direction. So fictional positive charges would be traveling in this direction. So they could move probably here and then here. Now, they could move here. This is the opening, right? The tricky part is that there is another battery in this situation. If the capacitor had no charge at all, that would be one situation. But this capacitor actually has a charge. How do I know it has a charge? Because of this equation. The capacitance is clearly not 0, and the voltage across the capacitor is not 0, it's 8. So, voltage times capacitance, charge. So, and we actually know, we are told that this plate is positive, this plate is negative. The voltage across the capacitor is 8, now at t equals 0. So, we could just redraw this circuit. A battery, a resistor, another battery, which right now has voltage 8, another resistor, the open switch. And if you look at this circuit now, what would be your answer? Yes, there is some curve. Because here we have a closed circuit with non-zero EMF. Any questions on this part? It's important. If we read the problem and it says the capacitor has no charge, we are told that there is no charge. In that case, that would be equal to 0. And in that case, that would not be the battery. That would be just the gap. And in that case, we wouldn't have any current in the circuit. But if we read and it says some potential across the capacitor, it means we can think of it as a battery. We can redraw the circuit. And after that, we can answer all the questions. So here, the equivalent circuit at t equals 0. That's important to understand because over time the voltage across the capacitor changes. Okay? So this is the equivalent circuit at t equals 0. And this is my next question. What do you think about the potential difference of the voltage across this resistor, this one? Question mark? All right. I've erased my drawings, but you should keep yours on. You know? And if you look at your picture, that gives you the answer immediately. On Wednesday, we started a class from a problem like that, 2 batteries. Yeah? So, what do you think is the voltage across the resistor page? I think. Thank you. And what do you think? So, 8, 16, 12, 24. Well, 8 and 16 are kind of more natural than 12 and 24, right? What do you think? All right. If you look, if you treat the capacitor as a battery, that gives you the answer immediately. This potential is 0, this potential is 24 because of this number. Well, we are told that this capacitor has the voltage 8. So 0, 8. 24 minus 8. Since we know that potential difference is 16 and we know the resistance, now we can apply the Ohm's law. So this current through the resistor A equals 4 amps. When? Only now. Only at t equals 0. Well, of course, we can ask a similar question about the potential difference across this resistor. And again, at t equals 0, it just has to be the same as the potential difference across the capacitor, which is 8. And now we can apply the Ohm's law to this resistor. Voltage divided by resistance gives the current here. And now we know all the currents. We just have calculated this current is 4, this current is 1. What does it give us for the current through the capacitor? It must be 3. But again, it is only now at t equals 0 because everything changes over time. Any questions? Well, we know how everything should end. Eventually, there is no current through the capacitor. Always, no matter how it starts, if we wait long enough, capacitor doesn't have any current anymore, eventually. Because the voltage stops changing, that means charge stops changing, no change in charge, no current. So, here, the initial value of the current is 3, but the final must be 0, always. That means this current decreases from 3 to 0. What about these two currents? Well, again, if we wait long enough, we can just redraw the circuit without a capacitor, because eventually the capacitor just becomes being a gap and doesn't do. We just can redraw the circuit like that. And this is a simple circuit. We can apply the Ohm's law. We can calculate the new current, the final current. It's just voltage divided by the total resistance, 2 amps. And this current is the same through both resistors. So the current A goes from 4 to 2, that means it decreases. The current B goes from 1 to 2, that means it increases. Any questions? Through logic. That's why it's a nice problem. Well, this is just a clear writing about what I did a minute ago. And what's going to happen, do you think, if we actually play with the switch? Back and forth, back and forth, back and forth. Well, again, actually, that's one more question to you. Yes? No? Q equals C times V. V equals R times I. Same letters. Does it mean they represent the same physical variables? If you think yes, press 1. If you think no, press 2. And now, I'm not going to give you 60 seconds for this question to answer. 17, 16, 13. Well, what do you think? Yeah. Well, you would have to say this question is ambiguous because, well, if we say it's a potential difference or it's voltage, yes, it's voltage. But if we say that one variable can be used only when we relate the charge and the capacitance, so one variable, this variable, cannot be related to resistor, it's related only to this capacitor. Another variable cannot be related to a capacitor, it can be related only to resistors. In that case, no. So, I trick you. Well, so, what's going to be happening? Well, let's just say that there is no current initially anywhere, and the capacitor has been discharged completely initially. So in that case, of course, we know that the voltage across the capacitor starts from 0. If I close the switch, the voltage should go up. Well, and in this situation, eventually, this voltage reaches the voltage across this resistor because they are in parallel. But if I don't wait for a long time, if I open the switch immediately again, what's going to happen? In that case, the capacitor is supposed to be discharging. So in that case, we're going to see something like that. But again, if I don't wait long enough, when it's completely discharged, I close the switch back, it should go something like that. So that is actually how we can start solving the problem from any reasonable value of the voltage across the capacitor, like we did in the minute before. Well, this is just a summary of all I've said about capacitors. And now we are going to a new topic, magnetic field. And again, let's start from some neat experiments. This is actually my first experiment. This is a vacuum tube. It has a source of electrons inside here, filament which emits electrons. You're going to do a lab with this exactly setup in tools. And if electrons are negatively charged, if I apply electric field in the region where electrons are, electric force will be accelerating electrons. So this power supply generates electric field between these terminals, these electrodes, and you can see the blue beam here. And that really makes it better. Well, next time just sit closer. You know what it is. It's a simple magnet. Every magnet has two poles. One we call north, another we call south. My question is, what's going to happen to this beam if I bring this magnet close to it? So, you can see it actually gets deflected. So, without magnetic field, electrons been traveling along a straight line, but now they're getting deflected. And the deflection actually depends on the orientation of this magnet. So, that means this magnet exerts a force on those electrons. And of course, the natural question is, what kind of a force is it? That cannot be a force of gravity. The mass is not large enough. No springs attached, no strains attached, so no friction. So it's supposed to be, and that's not electrostatic force. That's not a flamingo rough with torque. So it's a new force, and we have to study the property of that new force. And we actually can make another conclusion. So if this magnet is acting on beam of electrons, what do you think is going to happen if instead of using a beam of electrons, I'm going to be using a wire? This wire lies down between two poles of the magnet, north pole and south pole. So this magnet is acting in a way on this wire in a way like this magnet was acting on the electrons. So if I turn the power supply on, charge is going to be traveling through the wire. What kind of charges travel in wires? What kind of charges? What's the name for those charges? Someone, please. What kind of charges travel? Electrons. Of course. So I've been expecting immediate answer so that I could move on and don't spend much time on waiting for someone to say. Well, and we know magnetic field is supposed to be active on those electrons, exert some force. And that's what we're observing here. And you too. I'm turning on, and it starts moving. Magnetic field pushes out. Well, we actually can say something specific about the direction of current and magnetic field. Let's say, okay, so this is a positive terminal. That's a negative terminal. Okay. So the current travels from positive to negative. So when the current was traveling in that direction, the force was pushing it up. And if I use a simple compass, I can actually figure out which pole of this magnet is north pole, which is south pole. So, and it turns out this is a north pole, this is a south pole. So the direction from north to south, like this, current like that, force like this. This rule tells us how to figure out the direction of the force acting on any charges. We just have to, well, use our hand. I'm getting ahead of myself a little bit. This is the experiment we've done. You see, the direction from north to south is shown in terms of arrows. And we draw that arrow. If we draw a current, arrow, force. That's how these directions are related. By an agreement, by definition, the direction of those arrows from north to south outside of the magnet is taken as a direction of the magnetic field. Well, first of all, this region is special. If I take this magnet out, and now I turn the current on, nothing is happening to this wire. So, this region is special. To describe that speciality, we say there is a magnetic field inside. How do we check if there is or there is no magnetic field? For example, this way, we put a wire, we observe current, magnetic field presents. And in a similar way to electric field lines, we can use magnetic field lines to represent presence of magnetic field in the region. And here I have tiny iron filings in oil and a magnet. And if I insert a magnet inside, I can actually see magnetic field lines. Please take a look and pass it around. That's how they look like. This is basically a photograph of what's happening inside that thing. The difference between electric field lines and magnetic field lines is what? Magnetic field lines are loops. They don't end on charges. So it's always a loop like these, like these, like these. There is no break anywhere. And by a definition, the magnetic field inside the magnet points from a south pole of the magnet to its north pole. And since it's a loop, it should go back outside of the magnet, leaving the north pole and getting back in the south pole. And by some reason, some people are good at memorizing things. I'm not. So I had to invent a way to remember the direction of the magnetic field. So I say to myself, it's very cold at the North Pole. Nobody wants to live there, so everybody leaves it. So that's why magnetic field lines leave the North Pole. Well, there's many more pictures of magnetic fields. I actually have here a sample of the spore. This is a magnetite. That's what people found thousands of years ago at the magnet. Dig up and found that this thing actually attracts, well, not very strong, but if you look at the compass, it attracts it. Now, what we know about magnetic field and magnets. Any magnet always has two poles. So this is the magnet. How do we make a conclusion? It's a magnet, not just a piece of iron. Well, if we had a nail here, it would be attracted to both poles. But for the magnet, like poles repel, and opposite poles attract. And now if I break this magnet, and I check, it still has two poles. It still has a south pole, and it still has north pole. So no matter how small the magnet is, it always has two poles, and we cannot make them separately from each other, like charges. Well, and of course, the easiest magnetic field is the uniform magnetic field. The uniform magnetic field is magnetic field which is the same everywhere in magnitude and direction. And normally, between the poles of a magnet like that, the magnetic field is almost uniform. And if I have a magnet like that, I can use this magnetic field to, well, experiment with charges, travel through this. And this is what experiments show us. If we have a single charge traveling through a magnetic field, there is always a force acting, or almost always a force acting on it. The magnitude of this force depends on the magnitude of the charge, the speed of the charge, the strength of the magnetic field, and more importantly, people sometimes forget, on the angle between magnetic field and velocity. So if we want to change the magnitude of the force acting on a charge from magnetic field, we can do different things. We can change the strength of the field, we can change the speed of the particle, or we can change the orientation of the field or velocity. And the direction of the force is related to the direction of the velocity, the polarity of the charge, and the direction of the field by the right-hand rule. So this is the rule which textbook gives you. You use your palm, you curve fingers, and the thumb gives you the direction of the force. I personally don't like making two steps. This is my rule. Right hand rule. If you use your index finger and point in the direction of the velocity, well, more exactly saying the direction of the component of the velocity which is perpendicular to the field. And if you use these fingers to point in the direction of the magnetic field, the thumb shows you the direction of the force acting on a positively charged particle. So right hand cannot be used directly for electrons because electrons are negatively charged. It could be used only for protons or positrons. If you want to use a right hand rule for a negatively charged particle, you're supposed to use it and then you're supposed to reverse the direction. Or you can just use your left hand. Right hand for positive charges, left hand for negative charges. Positive, negative. So, velocity, magnetic field, force. And again, if you know 2 out of 3 directions, you always can figure out the third one. So, velocity field gives you force, force and velocity gives you field, force and field gives you velocity. Any question? Well, you know magnetic field and stuff is not a part of this common test. So, the last topic related to the test is capacitors. So now we kind of getting ahead. So on Tuesday in the morning, we have a review session. Please prepare the questions. On Wednesday in the morning, we're going to talk more about magnetic stuff. And on Wednesday night, the test. Thank you very much. Have a nice weekend. Yes.
I have.
So when time is 0, there is no voltage, and then voltage going eventually to the maximum value, which is equal to EMF of the battery. Now, for the voltage across the resistor, when time is 0, it equals to initial EMF, and then it gradually goes down to 0. And the current it always equals EMF divided by resistance. So for the current, we just have exactly the same expression. It starts from its maximum value, and then it decreases over time. And this product, RC, tells us how much time we should wait until the voltage drops. Then, well, E represents a specific number, 2.81 roughly. So if you wait exactly one time constant, that means your final voltage is initial voltage divided by 2.81. Well, it's exactly 8:50, so I'm gonna do on Friday some problems, but you know all the theory now and you can do almost problems on your own. And if you have any questions, you're welcome to office hours. Thank you very much. Have a nice day.